Fluid mechanics, viscosity, chapter 11, fluid mechanics, viscosity, okay? Okay? When a fluid, liquid or gas, flows, different layer moves with different velocity, giving rise to velocity gradient. Faster moving layer tries to accelerate the slower moving layer. Try to accelerate the slower moving layer. Okay? Okay. Faster moving layer tries to accelerate the slower moving layer. At the same time, the slower moving layer tries to retard the faster moving layer. This results in frictional force. Is that viscous force between any two adjacent layers in the relative motion. This property of the fluid, by the virtue which it opposes the relative motion between the adjacent layer, is known as viscosity. Knowledge of viscosity of liquid is useful in many fields. Oils are used in machine as a lubricant. Aeroplane or rocket moving through air, or submarines moving inside water. The lubricant should be such that its viscosity almost remains constant even if its temperature changes. Okay? Even if its temperature changes. Okay? If its temperature changes. Okay? Viscosity. What is viscosity? When the motion of a liquid over horizontal solid surface is slow and steady, its layer in contact with the solid surface is stationary. In other words, its velocity along the surface is zero. The velocity of any other layer is proportional to its distance from the stationary layer and is maximum for the topmost layer. If we consider any particular layer of the liquid, we find that the layer immediately above it is moving faster than the layer immediately below it. Okay? Hence, the upper layer tends to increase the velocity of the lower layer, whereas the lower layer tends to decrease the velocity of the upper layer. The two layers together tends to destroy their relative motion, as if there is some backward dragging force acting tangentially on the layer. Consequently, if a relative velocity is to be maintained, between the two layers of a liquid, an external force is required to overcome this backward drag. Okay? This property, by virtue which a liquid opposes the relative motion between its different layers, is called viscosity. Okay? The property by which a liquid opposes relative motion between its different layers. its different layer is called viscosity. Is called okay. The property by virtue of which a liquid opposes relative motion. A liquid opposes relative motion between its different layers is called viscosity. Coefficient of viscosity. Coefficient of viscosity. Coefficient of viscosity. Okay. Coefficient of viscosity. Okay. Let a layer Rs of a liquid move with a velocity small v relative to a parallel layer PQ. Okay. Parallel layer PQ. 1 minute. This is the layer RF. This is the layer RF layer. Okay. And its velocity is small v. Okay. This is S. And one layer is a PQ. Okay. And this is the distance y between the layers, and layer is moving around this. Okay. Okay. Then let a layer Rs of a liquid move with velocity v relative to a parallel layer PQ. Okay, which is at a distance x from it. Let the force on an area A required to produce this motion be F. This force F must act on Rs in the direction of motion. An equal force will therefore act on it in the opposite direction due to viscosity. This backward dragging force F depends upon the following factors. First point, F is directly proportional to minus V. Okay? If F force is directly proportional to the relative velocity V and act in a direction opposite to the direction of motion of the liquid. Okay? Then second point, force is directly proportional to area. Okay? Third point, force is directly proportional to 1 upon y. Okay? Combining all these factors we have, F is directly proportional to minus a v upon y. Okay? R. F is directly proportional to minus eta a v upon y, where eta is a constant depending upon the nature of the liquid and the coefficient of viscosity. Okay? Where eta is constant. Depending upon eta is constant depending upon the nature of the liquid, depending upon the nature of the liquid, depending upon the nature of the liquid, and is called the coefficient of viscosity, and is called the coefficient of viscosity. coefficient of viscosity. If the two layers are very close together, if the two layers are very close together, then denoting the distance between them by dy and relative velocity by dv, we get F equal to minus v eta a dv by dy. dv by dy is called the velocity gradient, where dv by dy is called the velocity gradient are the rate of change of velocity with distance. Okay, and a is 1 and dv by dy is 1, then f equal to n numerically, f equal to eta numerically, okay, then the coefficient of viscosity is thus defined as, the tangential force per unit area. The tangential force per unit area, okay. The tangential force per unit area required to maintain a unit velocity gradient is that a unit relative velocity between two layers is that a unit relative velocity between two layers a unit distance apart, okay. The tangential force per unit area required to maintain a unit velocity gradient. The tangential force per unit area required to maintain a unit velocity gradient is that a unit relative motion between two layers a unit distance apart, okay. Next point, unit, okay. Unit, okay. Unit. A fluid has a viscosity of 1 poise. A fluid has a viscosity of 1 poise if a tangential force of 1 dyne per square centimeter is required to maintain a relative velocity of 1 centimeter per second between two layers 1 centimeter apart. The SI unit of viscosity is decapoise, okay. The SI unit is standard, okay. International unit, SI unit of viscosity. SI unit of viscosity is decapoise, okay. Is decapoise, okay. A fluid has a viscosity of 1 decapoise if a tangential force of 1 Newton per square meter is required to maintain a relative velocity of 1 meter per second between two layers 1 meter apart. Okay. Now eta equal to force multiply distance between layers upon area multiply velocity. Then twice equal to dyne. Dyne multiply centimeter upon centimeter square multiply centimeter per second. Centimeter per second. Okay? Centimeter per second. And deca twice. Deca twice. Deca twice. Deca twice. Deca twice equal to Newton. Equal to Newton multiply meter. Newton multiply meter. Newton multiply meter upon meter square. Upon meter square. Meter square multiply meter per second. Meter per second. Meter per second. Okay? Equal to 10 to the power 5. 10 to the power 5 dyne multiply 100 centimeter upon 10 to the power 4 centimeter square multiply 100 centimeter per second. 100 centimeter per second. That is 10 dyne. 10 dyne. 10 dyne multiply centimeter upon centimeter square multiply centimeter per second. Centimeter per second. That is 10 twice. 10 twice. 10 twice. Okay? 10 twice. Is that show 1 deca twice. 1 deca twice. 1 deca twice. 1 deca twice equal to 10 twice. Equal to 10 twice. Okay? 1 deca twice equal to 10 twice. Equal to 10 twice. Dimension. Dimension. Okay? Dimension. Dimension. Okay? The dimensions of viscosity. Viscosity I proved below. Viscosity. Viscosity. Viscosity equal to force multiply distance between layers upon area multiply velocity. The dimensions of force is M1 L1 T to the power minus 2. And distance the dimensions of distance is L to the power 1 upon L square. Dimensions of area and dimensions of velocity is L1 T minus 1 meter per second. Okay? So the dimensions of viscosity is M1 L minus 1 T minus 1. M1 L minus 1 T minus 1. Okay? kg per meter second. Okay? Okay? Next, streamline and turbulent flow. Streamline and turbulent flow. Next heading, streamline and turbulent flow. Okay? Streamline and turbulent flow. Okay? Streamline. Streamline and turbulent flow. Streamline and turbulent flow. Okay? Next heading. Streamline and turbulent flow. Okay? Streamline and turbulent flow. Okay? Streamline and turbulent flow. You can listen carefully. You can show initially this figure. Okay? Okay? 1 minute. 1 minute. You wait just for 1 minute. Okay? Point A, point B, point C. Okay? The velocity at point A is V1. The velocity at point B is V2. You can let. Okay? And the velocity at point C is V. Okay? Then consider a liquid flowing. Consider, or you can listen carefully. Okay? Consider a liquid flowing in a pipe. Consider a liquid flowing in a pipe and let the velocity of flow V1 at V1 at A, V2 at B, and so on. Okay. Then if we time the velocity, if with time the velocity of at every point in liquid remains constant in magnitude as well as direction, then the flow is said to be steady. Then the flow is said to be steady. Okay. If with time, if with time the velocity at every point, the velocity at every point in the liquid remains constant in magnitude, constant in magnitude, constant in magnitude as well as direction, as well as direction, then the flow is said to be steady. Then the flow is said to be steady. Okay. Then the flow is said to be steady. In other words, in a steady flow, each particle follows exactly the same path and at the same velocity as its predecessor. Okay. As its predecessor. Okay. In a predecessor. Okay. In such a case, the liquid is said to have an ordinary or streamline flow. Okay. In such a case, the liquid is said to have an orderly or streamline flow, Okay. The line along which the liquid moves when the flow is steady is known as a streamline. Okay. Then you can show main definition. You wait just for 1 second. Please wait. Okay. 1 minute. The line along which the liquid moves. The line along which the liquid moves, when the flow is steady, when the flow is steady, is known as streamline. Streamline. Okay. The tangent at any point on this line gives the direction of the velocity of flow at that point. A streamline therefore represents a fixed path called or straight flows by an orderly procession of particles in tubes. In tubes of constant area of cross section, all the streamlines are parallel to the axis of the tube. The flow is streamlined only as long as velocity of the liquid does not exceed a particular value called the critical velocity. Okay? When the velocity is greater than the critical value, the flow of liquid does not remain steady but becomes turbulent. Okay? Okay? The flow is streamlined. The flow is streamlined. The flow is streamlined. The flow is streamlined. Flow is streamlined only as long as the velocity of the liquid velocity of the liquid does not exceed a particular value called particular value called the critical velocity. Okay? Critical velocity. The flow is streamlined. The flow is streamlined only as long as the velocity of the liquid does not exceed a particular value called the critical velocity. When the velocity is greater than the critical velocity, when the velocity is greater than the critical value, the flow of the liquid does not remain steady but becomes turbulent. Then the flow okay? When the velocity is greater than the critical value, the flow of the liquid does not remain steady. Okay? When the velocity is greater than the critical value, the flow of the liquid does not remain steady, does not remain steady, but becomes turbulent. Okay? When the flow is unsteady or turbulent, there are eddies and whirlpools in the motion, and the path ideal as the velocity of the particle are continuously changing. Okay? Next, critical velocity. To show the existence of critical velocity, experimentally consider a tube AB. About 2 centimeters in diameter, in which the liquid waters and carbon waters enters at sea. Waters enter at sea. Okay? Waters enter at sea. Okay? waters enter at C, okay, and leaves at D, and leaves at D. At the end of the tube, AB, at the end of the tube AB, there is a rubber rock. There is a rubber cork through which passes an inlet tube I, which passes an inlet tube I, drawn out into a cavity, I. Okay, drawn into a cavity I, drawn out into a capillary about 10 centimeter long and 0.5 mm in diameter. Okay, to show the existence of critical velocity, experimentally consider a tube AB about 2 centimeters in diameter, in which the liquid water enters at C and leaves at D. At the end of A, the tube AB, there is a rubber cork. Okay, there is a rubber cork. Okay, there is a rubber cork through which passes an inlet tube L, I, drawn out into a capillary about 10 centimeter, long and 0.5 mm in diameter, Okay, the tube I is connected to a reservoir. The tube I is connected to a reservoir containing ink. The flow of ink through it is controlled by a screw type pinch cock. Screw type pinch cock S. At C is connected a constant level tank, the position of which is so adjusted that water flow very slowly through the tube AB. Okay, very slowly through the tube AB. In this position, it seen that a long column of ink escapes from the jet along the central axis of the stream. Under this condition, the liquid is having a streamline motion. And all filaments move parallel to the axis of the tube. Okay, the head of water is slowly increased. So that the velocity of flow also increases. It is seen that beyond a certain velocity, the colored band of ink is broken up to eddies and mixes with water. This stage shows the turbulent flow. Okay, hence the critical velocity of a liquid is that velocity of flow above which the flow ceases to be streamline. Okay, critical velocity of liquid by the method of dimensions. Critical velocity of liquid. Critical velocity of liquid by the method of dimensions. By the method of dimensions. Okay, of dimensions. Okay, dimensions. Okay, The value of VC is critical velocity is found to depends upon the value of critical velocity VC is found to depend upon first point eta, the coefficient of viscosity, and rho, the density of the liquid, and r radius of tube, where eta is a coefficient of viscosity, coefficient of viscosity, and rho density of liquid, and r radius of tube, okay, radius of tube, okay. Hence the VC equal to k eta to the power alpha rho to the power v and r to the power c, where k is constant, okay. Substituting the dimension of the various quantities as we have LT minus 1 equal to M L inverse T inverse to the power A, and the dimensions of density M L to the power minus 3 to the power all to the power B, and L to the power C, okay. If you solve this, LT to the power minus 1, that make M to the power A plus B, L to the power minus A minus 3B plus C, and T to the power minus A, okay. According to the principle of homogeneity of dimensions, A plus B equal to 0, comma minus A minus 3B plus C equal to plus 1, and minus A equal to minus 1, okay. A equal to 1, comma B equal to minus 1, and C equal to minus 1. Hence VC equal to K eta by rho r. VC rho r upon eta equal to K. Okay. This constant K is known as Reynolds number. This constant K is known as Reynolds numbers. Reynolds number. Okay. Reynolds number. Okay. It is pure numerically and independent of the system of unit used. Okay. Its value is about 2000s, okay, and independence upon the system, okay. Significance of Reynolds numbers. Next, significance of Reynolds numbers, okay. Significance of Reynolds number. 1 minute. Significance of Reynolds numbers. Of Reynolds number. Okay, significance of Reynolds number. The significance of the equation Vc equal to k eta by rho r lies in the fact that non-dimensional quantity of the form VCPR upon eta determines the process that takes place during the motion of liquid through a tube, and when this quantity attains a certain value, the flow changes from a steady streamline flow to a turbulent one in which eddies are formed. Thus, the critical velocity of liquid is the first point, directly proportional to its viscosity. Thus, critical velocity of liquid, critical velocity of liquid is first point, directly proportional to viscosity, directly proportional to viscosity. Second, universally proportional to density, universally proportional to density. Third point, and universally proportional to radius of the tube, radius of the tube. Okay. It therefore follows the narrow tubes, low density and high viscosity help in producing orderly motion, and wide tubes, high density and low viscosity tends to produce a turbulent motion. Okay, high density and low viscosity Okay, high density and low viscosity tend to produce turbulent motion. Okay. Next point. Poiseuille's formula for the steady flow of liquid through narrow tubes. Okay, this heading is very, very important. Okay. Poiseuille's formula for the steady flow of liquid through a narrow tube. Okay. Poiseuille's formula for steady flow of liquid through a narrow tube. Poiseuille's formula for steady flow of liquid through a narrow tube. Okay. About 1940, French physicist Poiseuille derived the formula for the volume of liquid flowing per second through a cylindrical tube of a circular cross section. The derivation is based on the following assumptions. Okay, following assumptions. Okay, first point, assumptions. This is discovered in 1940 by French physicist Poiseuille. French physicist Poiseuille. Okay. assumption. First point. The flow is steady and streamline. Flow is steady and streamline. Okay. The streamline are everywhere parallel to the axis of the tube. The streamlines are everywhere. The streamline are everywhere parallel to the axis, parallel to the axis of the tube. Parallel to the axis of the tube. Second point. The pressure over any section. The pressure over any section. The pressure over any section normal to the axis. Normal to the axis of the tube. Is constant. So that there is no radial flow. Okay. The pressure over any section normal to the axis of the tube is constant, so that there is no radial flow. Okay. Third point. The liquid layer in constant with the valves of the tube is at rest, and the velocity of any layer of the liquid is only a function of distance of the layer from the axis of the tube. Poiseuille determine the viscosity of liquid by measuring the volume of the liquid flowing through a capillary tube. Okay? Capillary tube. The liquid layer in contact. The liquid layer in contact with the walls of the tube is at rest, and the velocity of any layer of a liquid is only a function of distance of the layer from the axis of the tube. Okay. 1 minute. Poiseuille determined the viscosity of a liquid by measuring the volume of the liquid flowing through a capillary tube. Theory. Consider a capillary tube. Length L and radius small a. Okay, and radius small a. If the flow of the liquid through it is steady. The velocity of the liquid along the walls is zero. The velocity of liquid along the walls is zero, and maximum along the axis of the tube, and maximum along the axis of the tube. Okay. Consider a cylindrical. Consider a cylindrical layer of the liquid coaxial with the tube of inner radius r. Consider a cylindrical layer of the liquid coaxial with the tube of inner radius r and outer radius r plus dr. Shown separately, the velocity of a liquid at a distance r. The velocity of the liquid at a distance r from the axis of the tube is v. From the axis of tube is v, and at a distance r plus dr, the r plus dr is v minus dv. So that dv by dr is the velocity gradient. So that dv by dr is the velocity gradient. Okay. One minute. The surface area of the cylinder. The surface area of the cylinder is 2 pi RL. Okay. The liquid and the surface area of the cylinder 2 pi RL. The liquid on the inner side of the cylindrical layer is moving faster, while that on outer side is moving slower. Okay. The tangential force exerted by the outer layer and the inner layer opposite to the direction of motion is given by F equal to minus eta 2 pi RL dB by dr, where F is tangential force. Tangential force, okay, exerted by outer layer and the inner layer. Exerted by the outer layer on the inner layer opposite to the direction of motion is opposite. Inner layer opposite. Okay. The forward push due to different pressure P on the two sides of the cylinder of radius r. The forward push due to the difference of pressure P on the two sides of the cylinder of radius r equal to P multiply pi r square. Okay, 1 minute. When the motion is steady, There is no acceleration of the liquid, and thus we have, when the motion is steady, when the motion is steady, when the motion is steady, there is no acceleration, there is no acceleration, there is no acceleration of the liquid, of the liquid, and thus we have, minus eta 2 pi RL dV by dt equal to P pi R square. Okay, then dV equal to minus P by 2 eta L into R dr. Okay, integrating both sides, we have V equal to minus P by 2 eta L multiply R square by 2 plus C, where C is constant integration, where C is constant integration, constant integration. Okay, but as the velocity of the liquid along the side of the tube is 0, therefore R equal to A. Okay, but as the velocity of the liquid along the sides of the tube is 0, but as the velocity of the liquid along the sides of the tube is 0, therefore if R equal to A, then V equal to 0. Substituting this value, we get 0 equal to minus P upon 2 eta L multiply A square by 2 plus C. C equal to P by 2 eta L multiply A square by 2. Okay, hence V equal to P by 4 eta L A square minus R square. This is equation number 3. Okay, and this is equation number first. Okay, and this gives the velocity of flow at a distance r from the axis of the tube through the cylindrical layer. The area of cross section of cylinder layer of the radius r and thickness dr equal to 2 pi r dr. 1 minute. The area of cross section of the cylinder layer of the radius r and thickness dr. You let this is the cross section of cylinder, and this is the center O, and this is the radius A, and this is the radius R, and this is radius dr. Okay, volume of liquid passing per second. So volume of liquid passing per second through this area dV equal to V into 2 pi r dr, because area of cross section of cylinder layer of radius r and thickness br equal to 2 pi r dr. Okay, hence the volume of the liquid passing through the whole tube per second is given by dV equal to integration of 0 to a 2 pi r v dr. Okay, then V equal to 0 to A P by 4 eta L A square minus R square 2 pi R dr. Okay, then pi P upon 2 eta L integration of 0 to A square R minus R cube dr, that is pi P upon 2 eta L A square R square upon 2 minus R to the power 4 by 4 0 to the 0 to A. This is equation number second. This is equation number second. Okay, this is equation number second. Then pi P upon 2 eta L A to the power 4 by 2 minus A to the power 4 by 4. Okay, if solve this equation, then pi P A to the power 4 upon 8 eta L, then eta equal to pi P A to the power 4 upon 8 LV. Okay, thus we know P, A, L and B are the coefficient of viscosity can be determined. Okay, and this is the poiseuille's formula for the flow of liquid through the capillary tube. It is true only for streamline flow. It is true only for streamline flow. Streamline flow. Okay, the flow is streamline as we know when the average velocity of flow is less than the critical velocity, but the critical velocity is inversely proportional to the radius of the tube. Hence the above formula fails in case of tube of wide bore. Okay, and moreover the pressure difference between the ends of the tube should be small in order to have a streamline flow. Okay, next heading, Poiseuille's flow method for determining the coefficient of the viscosity of a liquid. Okay, next heading, Poiseuille's flow method for determining the coefficient of viscosity. Okay, formula V equal to pi P A to the power 4 upon 8 eta L. Okay, eta equal to pi A to the power 4 upon 8 L P by V equal to pi rho G A to the power 4 upon 8 L into H by V. Experimental arrangements. Experimental arrangement. Okay, along narrow capillary tube C of uniform bore is placed horizontally, having its end inserted into two unions U and B. The experimental liquid say water. Experimental liquid say water. The experimental liquid say water is allowed to enter the capillary at union U at a constant pressure by making use of constant level apparatus A. Constant level apparatus A. Okay, the liquid will be leave the capillary through the other union B, from where it can be collected in a measuring jar. A pinch of cork regulates the flow. Unions are connected to manometer M. By means of two rubber tubes. The difference H between the level of liquid in two leaves of a manometer M gives the pressure difference between the ends of the capillary tube, you can show. Okay, procedure 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 with the help of the pinch cock K, with the help of pinch cock K, the flow is adjusted so that the liquid leaves the capillary tube drop by drop. Capillary tube drop by drop. When the flow becomes steady, the emerging liquid is collected in a graduated jar for a certain intervals of time. Thus we find volume V. Thus we find volume V flowing per second for a constant difference of levels H in the manometer. Okay. The experiment is repeated a number of times for a different value of H. A graph of V against H is plotted and the average value of H by V is determined. The length and radius of the capillary tube are determined in usual manner. Okay. Then the value of neta at room temperature is calculated using the above formula. Okay. Using the above formula. Next heading, main source of error and corrections applied to Poiseuille's formula. Next heading, main sources of error and corrections applied to Poiseuille's formula. Poiseuille's formula. Main sources of error and corrections applied to Poiseuille's formula. Okay. In deducting Poiseuille's equation, the following two factors have not been considered and therefore same correction are necessary. First point, length. When the liquid enters the tube, its motion is accelerated at the inlet end, and as a result of this, the velocity distribution becomes uniform and streamlined. Only when the liquid has traveled a short length of the tube, this necessitates a correction for the effective length of the tube from L to L plus 1.64 A. Okay. Second, pressure. When the liquid leaves the tube, it has some velocity. Hence, the entire pressure difference P equal to H rho G is not used up in overcoming the viscous resistance, but a part of it is spent in imparting kinetic energy to the liquid. The effective pressure is less than the actual pressure by an amount of V square rho upon pi square A to the power 4. Okay. Hence effective pressure. Hence effective pressure P1 equal to H rho G minus V square rho upon pi square A to the power 4. Substituting the value of P1 instead of P. In Poiseuille's equations, we get substituting the value of P1, instead of P in Poiseuille's equations. In Poiseuille's equation. equation. Okay, we get eta equal to pi a to the power 4 h rho g upon 8v1 plus 1.64 a minus v rho upon 8 pi l plus sorry, this is l plus 1.64 a. Okay, this is the corrected version. 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 Okay. Next heading, parabolic nature of velocity profile. Next heading, parabolic nature of parabolic. Next heading, parabolic nature of velocity profile. Okay, parabolic nature of velocity profile. Okay, this you can show by the help of this figure. Okay, you can show this. 1 minute. dV by dr equal to 0. Okay, the velocity of a liquid flowing through a uniform capillary tube. V equal to P upon 4 eta L A square minus R square. So that velocity of flow at a distance R from the axis of the tube through the layer is a parabola. You can show this figure. Okay, hence the velocity profile is parabolic in nature. Hence the velocity profile. Hence the velocity profile is parabolic. In nature. Okay. Next heading, variation of viscosity. Variation of viscosity of liquids, gases with temperature. Okay, with the temperature. Okay, variation of viscosity of liquid gases with a temperature. The viscosity of liquid decreases with temperature. Viscosity of water decreases from 0.0101 poise at 20 degrees Celsius to 0.0047 at 60 degrees Celsius. Viscosity of liquid decreases. Viscosity of liquid decreases when temperature increases. Temperature increases. Okay, the viscosity of water. The viscosity of water. 0.0101 poise at 20 degrees Celsius to 0.0047 at 60 degrees Celsius, and that of castor oil from castor oil from 24.18 poise at 10 degrees Celsius to 9.86 at 20 degrees Celsius. No definite relation has been found to exist between viscosity and temperature, but Various empirical formula have been suggested from time to time which are all approximate. One of these relation has the form log eta equal to a plus b by capital T, where a and b are constants, constant, and T is absolute temperature. Capital T is absolute temperature, okay, absolute temperature. In the case of gases, the viscosity increases with temperature, okay, and in the case of gases, in the case of gases, viscosity is increases with temperature, okay, temperature. That means if the temperature of gases is increases, then viscosity is increases, okay. According to the kinetic theory of gases, the variation of viscosity with temperature is given by eta equal to a eta naught T to the power 1 by 2. According to kinetic theory of gases, kinetic theory of gases, okay, according to kinetic theory of gases, okay, where a is the constant, okay, a is the constant, and neta naught is the viscosity at 0 degree, viscosity at 0 degree, and T and capital T is absolute temperature, at which the viscosity is eta, okay. So Sutherland taking into consideration the small force of attraction between the neighboring molecules, modified the formula to eta equal to eta naught a T to the power 1 by 2 upon 1 plus capital S by capital T, okay, where S is known as a Sutherland constant, okay, Sutherland constant. For small ranges of temperature, this formula hold true for many gases, okay. Small temperature, for small ranges of temperature, this formula holds for many gases. This formula holds true for many gases, okay. Variation of viscosity with pressure. Next, variation of viscosity, variation of viscosity with pressure, variation of viscosity with pressure. The viscosity of liquid in general increases with increase of pressure, okay. The viscosity of liquid in general increases, the viscosity of liquid increases with increase in pressure, okay. And for example, the viscosity of ether, the viscosity of ether. Viscosity of ether at 20 degrees Celsius is raised by about 60% when pressure is increased to 500 atmospheres. When pressure is increased when pressure is increased to 500 atmosphere. Okay. In case of water at normal temperature, there is decreases in viscosity for the first few hundred atmosphere. Okay. And in case of water, normal temperature, there is decreases in viscosity for the first few hundred atmosphere. For more viscous liquid, the increase in viscosity with pressure is much more than in case of fairly mobile liquids. Okay. For moderate pressure, the viscosity of a gas is found to be independent of pressure, but at very high pressure, the viscosity increases with increase in pressure. Okay. And in moderate pressure, the viscosity of gas is found be increases if pressure increases, but at very high pressure, but at very high pressure, but at very high pressure, the viscosity increases with increase in pressure. The viscosity increases with increase in pressure. Okay. Viscosity increases with increase in pressure. Next, studying equation of continuity.